Hello, in this video I'm going to teach you about the electric field. So first, before I teach you about the electric field, I need to teach you what a field in general is. So in physics, a field is a region of space where every point has an associated value. That's kind of abstract, so here's a concrete example to help you visualize it. Okay, so let's say that there is a room, any room, classroom, and on one side there's a heater, and on the other side there's an air conditioner. So the heater makes things hot and the air conditioner makes things cold. If you took any position in this room, so right here, or here, or here, or here, you could get a temperature, and you would have a different temperature for every point. Maybe near the heater it's hot, like maybe at this point it's like 80 degrees, but near the air conditioner it's like 60 degrees. If you looked in the middle, like right here, maybe it would be 70, maybe right here it would be 64. It doesn't really matter what the temperatures are. What matters is you can take literally any point of this room and get a temperature value associated with it. So the temperature in this room is actually a temperature field, because every single point has its own temperature. So a field is a region of space where every single point has a value. It could be a temperature value, it could be an electric field value, it could be a magnetic field value, doesn't matter. Every point gets one. So the electric field is like a temperature field, but it's not a scalar field. The electric field is a vector field. And that means that in every single point, instead of having a number, like 20 degrees Celsius, it gets a vector. And remember, we can represent vectors as a bunch of arrows. So you can imagine the electric field as basically being a bunch of arrows. There's an arrow on top of every single point in the entire universe. Right here above my head, there's an electric field vector pointing in some direction. Right there above your head, wherever you are, there's an electric field vector pointing in some particular direction. So some possible electric fields in a room. Maybe you have a room and the electric field vector points down everywhere. That's fine. Maybe it points to the right everywhere. That's okay. Maybe one points up everywhere. Or maybe they're all moving away from a certain object in the middle. Well, an electric field is basically just a bunch of vectors. Every point gets a vector. So there's a value for the electric field at every possible point of the universe. But some real physical thing actually makes these vectors appear and arrange themselves into patterns. It's not like you can randomly choose a vector for every point. It has a specific vector because of the physical objects around it. We call this thing that actually makes the vectors appear electrical charge, and we measure it with the unit coulombs. So electric charges are the physical objects that control the electric field vectors and make them point in specific directions. So there are two different ways that a real physical object can affect the electric field. It can make outward-facing arrows around it, and we call this a positive charge. So positive charges create outward-facing field vectors, and it can also make inward-facing arrows. And if it makes inward-facing arrows, we call this negative charge. So if a physical object creates outward-pushing field vectors around it, we call it positive, and if it creates inward-pulling field vectors around it, we call it negative. So positive and negative charges are different because they create different kinds of vectors in the electric field. Positive charges create outward-pushing arrows, and negative charges will create inward-pulling arrows. So that's one difference, the kind of arrows they make. But that's not the only difference between positive and negative charges. They create different vectors, but they also respond differently to the vectors that are already there. So positive charges, they're going to move in the same direction that the vectors tell them to move. For example, if you have a positive charge, then you turn on an electric field around it, it's going to sort of feel the vector that it's on top of, pointing to the right, and say, yeah, okay, I'll go to the right. So the positive charge is going to move in the same direction as the electric field vector. But negative charges are like rebellious teenagers. They're going to move in opposite directions. So you have a negative charge, you turn on an electric field, it sort of senses that there's a rightward pushing arrow under it, and it says, no, I'm not going to go to the right, I'm going to go to the left. So it does exactly the opposite of whatever it's told. So this results in some cool behavior. For example, opposite charges are going to pull together, and similar charges are going to be pushed apart. Like two negatives are going to be pushed apart, and two positives will also be pushed apart. And this is because of the fields they make. Let's just think it through. A positive charge creates outward pushing arrows, right? And if you put another positive charge right there, it's going to sense the arrow under it pointing to the left, in this case, and say, okay, sure, I'll go to the left. And it goes to the left. Same thing will happen if you have two negatives. But if you have a negative and a positive, what happens is the positive creates these outward pushing field vectors, and the negative charge sort of feels this vector pointing to the left and says, no, I don't want to go to the left, I want to go to the right. so it goes in the opposite direction, which is moving it towards the positive charge. So there's some objects that aren't affected at all by these electric field vectors, and we call these objects neutral. There are two different ways that you can be neutral. The easiest way is you can just have no charge at all, like a neutron in an atom, or you can have an equal amount of positive and negative charges sort of glued together in the same object, like an atom itself, or like a block of wood. If something has no charge at all, then you can put it in an electric field and it just won't feel it. It won't even sense the arrow under it. It doesn't matter, so it doesn't move at all. And if you have equal amounts of opposite charges, like you have 3 positive and 3 negative charges together, it'll be pulled equally to the right and to the left, and so it'll be like a tug of war, where no side wins and it doesn't actually move. So finally, we got to get to the math of the electric field. There's a mathematical formula you can use to calculate the force that 2 electrically charged particles will pull or push each other with. That force is this: F equals K Q1 Q2 over R squared. Let me explain what these are. So F is clearly the electric force that's pulling or pushing them apart. Q1 is the electric charge of the particle that's responding to the electric field. So we have 2 particles. One of them is making the field, the other one is responding to the field. Q1 is the electrical charge of this particle. Maybe it's positive 1 or negative 2. Q2 is the charge of the other particle, the one creating the field. And it doesn't actually matter which one you decide is responding and creating. If you have 2 particles, just choose one of them to be Q1 and the other one to be Q2, and it'll be right. R is the distance between the charges. It's on the bottom because distance and force are inversely related. So that means that if they're very far apart, they're not going to pull very strongly. But if they're close together, they're going to pull very strongly. And then K is called Coulomb's constant. We use it because the units that human beings use are not really the units that the universe likes. It's equal to the number 9 times 10 to the 9th. It's just a number when you're using standard units, like newtons, meters, and coulombs. So one last thing. If F, the force you calculate, is a positive number, then that means that the charges are repelling each other. For example, you're going to have a positive force with Q1 being positive and Q2 being positive, which means that 2 same charges, they repel. Or you could have it with Q1 being negative and Q2 being negative, because like negative 1 times negative 1 is positive 1. So if F is a positive number, that means that Q1 and Q2, the objects, they have the same charge, and that's going to make them repel. But if the force is negative, that means that Q1 is positive and Q2 is negative, or the other way around. And so they have opposite charges, so they will attract. So a positive force means that they're pushing, and a negative force means that they're pulling. So here's a review of everything we learned. Positive charges make outward pushing vectors. Negative charges make inward pointing vectors in the electric field. Positive charges, they do what the arrows tell them to, and they move in the same direction. Negative charges move in the opposite direction of the electric field vectors. If 2 electric charges have the same sign, so positive and positive, or negative and negative, they're going to push away from each other. But if they have opposite signs, like a positive and a negative, they will attract. Objects with the same amount of positive and negative charges inside them, like they have the same positive and negative charge just in different parts, they act like they're neutral because electric fields push and pull them in opposite directions, and it's like a tug of war where they're tied. And finally, this is the formula they use to calculate the force pulling or pushing 2 electrically charged objects. K is just a number. It's 9 times 10 to the 9th when you're using normal units. Q1 is the charge of the first object. Q2 is the charge of the second object. And R is the displacement vector between the charges, which is just how far apart they are. And it's squared on the bottom. So if you plug some numbers in here, you can calculate the force in between 2 charges. That was everything. I hope it was helpful.